All right, so today we're going to be talking about estimating parameters and determining sample sizes. So up at the top here, I've got a lot of definitions. I'm not going to go through all of them because y'all can read. But I do want to stress on a couple things. One, on point estimate, the key part of this definition here is single value. So anytime you have an unbiased estimator, so proportion, mean, variance, you're going to have basically the sample statistic being the point estimate of the parameter. Remember that statistic is for the sample, parameter is for the population itself. So we are going to be looking at confidence intervals, and we will swing back around to confidence intervals as we're doing hypothesis testing in the remaining chapters. So it's important to understand what a confidence interval is, and it's going to just give us a range, so an interval. Confidence levels, the fill in the blank here, because we have common confidence levels of 90%, 95%, and 99%, those are our alphas. So it says probability 1 minus alpha. So a lot of times they'll give you the confidence level as a percent. There are other times when they actually just give you the alpha. So you really need to know how to do that both ways, and that alpha equals 0.1 would correspond with a confidence level of 90%. Alpha equals 0.05 would be 95%, and alpha equals 0.01 would correspond to the 99%. So just make sure you understand that really those are asking for the same thing, just in a different way. Also, on the critical value, the key here is the z sub alpha over 2. So make sure we understand that it's not z sub alpha. So if they give you alpha, you have to divide that by 2 in order to find that critical value. Margin of error uses the z sub alpha over 2. It also uses p hat and q hat, where p hat and q hat are complements. Requirements in order to use a confidence interval to estimate a population proportion. So sample has to be a good sample. So we need it to be some sort of simple random. We have to have the conditions for the binomial distribution. So same ones that we've already talked about that are listed in number 2. And then we have to have at least 5 successes and at least 5 failures. When we write a confidence interval, there are 3 different ways to do so. So we have inequality format. We have literally, we usually just call this p hat plus or minus e format. And then this last one is interval format. So this is interval. This goes by its own name. This would be the inequality format. When we have confidence intervals, the general rule for proportions, which is what we're discussing right now, is to round to 3 significant digits. So you know that throughout the course we've got various rounding rules. So here is the rounding rule for our proportion confidence intervals. Sometimes we're going to be asked to work backward, meaning that we know the confidence interval and we're trying to find p hat and e. So meaning we want to know the point estimate and we want to know what the margin of error is. When we do the examples, you're going to see why these work, but they're very similar to each other. So for p hat, you add the 2 limits together and divide by 2. For the margin of error, you take the upper minus the lower and divide by 2. The last set of formulas here is when we know, or sometimes don't know, our estimate for p hat, and we're trying to figure out the sample size. So a situation for this might be where we want to figure out how many people or items we need to test in order to have accurate results to the level of confidence that we want. So if I know that I want to be 99% confident in my results, then I might have to work backward with this formula to figure out, okay, well then how many people do I have to have in my study? So that's what these guys are for. All right, so let's get to the examples. So in example 1, we're given a confidence interval that's in inequality form. We're told that P is between 0.0641 and 0.186. And we are then asked to convert it into the P hat plus or minus E format. So this one kind of gives us two examples in one because it is converting from one format to another, but this would also give us the procedure for if they gave us the confidence interval and asked us just for one of these individual values. So if they only asked me for P hat or only asked me for E. So in this case, I know, because I know when I look at inequality format up here, so that the left-hand side is P hat minus E and the right-hand side is P hat plus E. So if I want to find the point estimate, I'm going to take the upper plus the lower and I'm going to divide by 2. So the upper, so P hat equals 0.186 plus the lower, 0.0641 divided by 2. And then for E, I can use the same idea from the formula that we have up here, and that's going to allow me to do upper minus lower divided by 2. So 0.186 minus 0.0641 divided by 2. Now, there are other ways to manipulate other than just using those straight formulas. Once you have P hat, you could just take your P hat minus the lower limit to get E. So there are options, and if you get the same answer and you show your work, that's obviously fine. So in this case, in the calculator, when I add and divide by 2, and that's going to give me 0.125. So that's my P hat. My E, 0.186 minus 0.0641 is going to give me 0.0610. So I'm not done with the question because it asked me to write it in the form P hat plus or minus E. So the confidence interval written in that format is 0.125 plus or minus 0.0610. So what this is really saying is that this was our sample estimate. We're guessing that our margin of error, that this might be off by about this amount, plus or minus, meaning it could be bigger by that amount or smaller than that amount is what it's trying to say. All right. Example 2. From a 3M privacy filters poll in which respondents were asked to identify their favorite seat when they fly, 492 of 806 chose the window seat. So that's our background information, and it asks us here for several things. So part A, what is the best point estimate of the population proportion? So again, definitions, we've got them here for a reason. We need a single value, and we know that P hat is the best point estimate of P. And this question is indeed asking me for P. It's asking for the population proportion. So that means that what I need to find is P hat here. P hat is the proportion of the sample. So that's exactly what we're given here. We just have to put it in the right format. We know that 492 of 806 chose the window seat. So 492 of 806, this is going to give me my p hat, which gives me 0.610. Next one, find the value of the margin of error for a 99% confidence interval. So margin of error formula, when I don't have the confidence interval already, which here clearly I do not. So I'm going up and I'm going to be using this formula. So I need z sub alpha over 2, I need p hat, q hat, and n. So z sub alpha over 2 is the one I'm going to have to find first. So when it's a 99% confidence interval, remember that that means that we have to use the correct value. So z sub alpha over 2 is going to be based upon these values that we had with the critical values. So it says an area of alpha over 2 on the right tail. So this is a normal curve. 99% means that alpha is 0.01. So if alpha is 0.01, then in this case, 0.01 divided by 2, z sub alpha over 2 is the z-score that I'm going to get when I have this picture. 0.01 divided by 2 is 0.005. So it's saying that that's the area that's on the right of my actual z sub alpha over 2. So I want to find the actual score. What I know is this area. Now, again, depending on what calculator operating system you have, if you have the one that allows you to choose right, then by all means, go ahead and do that. Most of the operating systems still, you have to give the area that's on the left side. So that, of course, means that we're going to have to do 1 minus in order to figure out what goes on the left. So that means that we've got 0.995 as the area on the left, and the way that we find z-scores when given the area is by doing inverse norm. So we're going to do inverse norm of 0.995. It does say we're using the normal curve, so we're using 0 and 1 as the standard normals. So if I bring my calculator over here, second distribution, choose choice 3. Set your area as 0.995, mean and standard deviation is 0 and 1. And then it will give you the z-score. Now remember, we round z-scores to 2 decimal places. So sometimes the book will carry more, but since it's a z-score, we really should just do the 2. So 2.58 would be our value here. Now you will start to notice you're not always going to have to show this work, because what's going to happen is that your z sub alpha over 2's, because we constantly pretty much use the same confidence intervals, is that you'll actually just start to have those z sub alpha over 2's memorized. I wanted to fully explain it so that you know how to find it in case you don't get them memorized. But for a lot of you, you'll just know what it is, and that's great. So now I have z sub alpha over 2. I also need p hat and q hat. So in this case, we already found p hat here. So then I just need q hat, which would be 1 minus 0.61, which gives me 0.39. So now I have all of the pieces of the formula. So margin of error equals z sub alpha over 2 times the square root of p hat, which is 0.61, times q hat, which is 0.39, all divided by n, the sample size, which is given to us in the original problem, so that's 806. And so then, of course, we can just type this whole thing into our calculator, and we should get 0.0443 approximately. So there is our margin of error. So next, it asks us to use a 99% confidence interval to estimate the proportion of the population who chooses the window seat when they fly. So I'm going to show you how to do this both by hand and in the calculator. Obviously, both are acceptable, but if you're going to use the calculator, make sure that you're writing your commands out as we go. So by hand, in this case, because we already have our p hat and our e, we could do p hat minus e and p hat plus e, and that would give us our value. In this case, we're going to use interval notation because that's the most common one. So if I do p hat plus margin of error, that would be 0.61 plus 0.0443, and then p hat minus my margin of error, 0.61 minus 0.0443. So those individual values then we can do on our calculator here. Maybe I can find it. There it is. Okay, so we've got 0.61 and we're going to add 0.0443, and that gives us 0.6543. And typically, because we round in the introductory information, I said we'd round confidence interval limits to 3 decimal places. So in this case, it'd be 0.654 only is what we would use. So 0.654 here. And then for the other end, we have 0.61 minus the standard or the error. And so we get, if I round it, 0.566. So that would mean that in an interval notation, I would have 0.566 to 0.654, and this would be my answer. That is in interval format, a confidence interval that goes with 99% confident because I used the correct z sub alpha over 2 to go with it. On the calculator, we have lovely buttons to press for this. So in order to do this, I'm going to have you write it down, and then obviously I'm going to show you as well. But you're going to go to Stat, and then you're going to choose Test. So we'll get that far. So Stat, Tests, and then we're going to learn almost every single test that is in here by the time we finish this course. But the one that we're using right now is going to be choice A. So you can either scroll down or scroll up. I think in this case, it's about the same distance regardless. So choice A here, you can also press alpha A if you want. But we're choosing one prop z interval. So that stands for one proportion. The z is because we're using z-scores, an interval because it's a confidence interval. So we're going to choose that. Once we do that, it prompts us that we need x, n, and our confidence levels. So over here, we went to Stat, Tests, we did choice A, which is one prop z interval. And then what we are going to input now is what it's asked me for. So it wants x, n, and our confidence level. So we type in X, remember, is our total number of successes. N is our total sample size. So 492 out of 806. Confidence level, you always just give the percentage as a decimal. So in this case, 0.99. So once we do that, I'm going to go back over here and just type that in because this is how you would write it on your paper. 492, 806.99. Now, of course, as you work on the paper, if you're using the calculator, you'd really only need this part. You don't need to write out stat tests choice A. That's just in your notes so you remember how to find it. So once you have this, then you can go ahead and press calculate. And you can see that it gives you more decimal places than you need. It also gives you your p-hat value, which is helpful. So notice here we get 0.566 and 0.655 if we're rounding. So it's almost exactly the same, but notice that we do have just one little decimal point that's off here. Again, that's totally fine, but this is why it's important that you show work. So we know that you got this answer because you did it by hand, or you got this answer because you did it on the calculator. All right, here is the part that is tricky for everyone. We are getting into confidence intervals, and then we're getting into hypothesis testing after that. Both of these things have a very specific script that has to be followed in order to interpret. Like when you write your conclusion, it has to be written in a certain way. Hypothesis testing even more so than the confidence intervals. But the interpretation, we do the same wording-ish each time. So we say we are, and then whatever the percentage is, in this case 99. So 99% confident that, and then you say the population and then whatever statistic you're talking about. In this lesson, we're only talking about proportions. So we would say population proportion. And then you describe proportion of what? What are we talking about here? So in this case, we're talking about people who prefer the window seat. And then you give the actual intervals. And so we would say is between 0.566 and whichever one we're using. We'll just use the calculator one. So we always say we are, whatever the percentage is. You describe which parameter we're discussing, in this case population proportion, but eventually we might have population mean or population variance. And then we describe the situation, what we're talking about, and then we give the limits. All right, last one. Example 3, you plan to develop a new software system that you believe will surpass the success of Google and Facebook combined. In planning for the operating system that you will use, you need to estimate the percentage of computers that use Windows. How many computers must be surveyed in order to be 99% confident that your estimate is in error by no more than 1 percentage point? So we are going to do this 2 different ways. First way, assuming that nothing is known about the population. So meaning that there's no background studies that have already been done that tell us approximately how many computers are currently using Windows. So this here, we're trying to find sample size. So we're looking at these formulas here. So the first one, A, is we don't have a point estimate. So what we do is we take z sub alpha over 2 and we square it. We multiply by 0.25 and then we take that over the margin of error squared. So in this case, the margin of error we get right here. Sometimes they might actually tell you, an E, but sometimes they're sneaky about it and they do something like this. So I used 99% again so that we wouldn't have to redo a z sub alpha over 2. So we're doing the exact same z sub alpha 2 over 2 that we used before. So we know that n is going to equal 2.58 squared times 0.25. The 0.25 is because if we know nothing about the proportion, we assume that it's 50-50. And so 0.5 times 0.5 is 0.25. So that's where that came from. They're not just making up random numbers. So the 1 percentage point means that we're saying E is 1%, which is 0.01. So E squared is the bottom of this formula, so we would say 0.01 squared. And so then we just type this whole thing into the calculator, which gives us, let's see, hold on one sec, 16,641. So you can see I just typed it all in just like it was. This one happens to come out as a whole number, and so we can say 16,641 would be the number of computers that we would need to survey in order to be 99% confident. If we change the confidence level, that would change our z sub alpha over 2, which would save some of these values. So the less confident you want to be, the smaller the sample size needed. So B, assume recent survey suggests that 90% of computers use Windows. So if that's the case, then we're going to use the other formula where now we have a P hat, which means we can figure out a Q hat, and we just make adjustments based on that. So N equals, of course, this part stays the same, but now P hat is 0.9, which means Q hat is 0.1 over our 0.01 squared. So if I go back to the calculator then, I'm just going to go up and copy this guy and then change the top. Maybe. There we go. 0.9 times 0.1. And everything else should be the same. So then once you've got that all typed in, compress enter, and this time we get a decimal. So 5,990.76. Notice that this is a drastic change. When we know something about p hat, that is going to drastically change our sample size. The other thing that's true is you have to be careful. This one's a 0.7, so you would round it up anyway, but you can't survey a part of a computer. You either survey the computer or you don't. And in this case, even if this number were not bigger than 5, we would still need to bump it up, because what that would be saying is that 5,990 isn't quite enough. So you always have to bump it up to the next whole number. So in this case, we'd have 5,991 for the total number of computers we would need to survey there. All right, I think hopefully that gives you everything you need to feel like you can be successful in the practice problems. Make sure you check in with your teacher for questions.